So, ladies and gentlemen, esteemed colleagues, thank you very much for coming, despite the snow situation in Hungary. And I will speak about, as the title suggests, about categorical equivalences for residuated lattices, especially a work of mine, but it will be in the end. Before we get there, I'm going to speak about some preliminary results about categorical equivalences, so that you can situate the results in the vast landscape of residuated lattices. Well, for what is the basic definition is a residuated lattice. These are algebraic semantics of so-called substructural logics. And the residuated lattice is an algebraic structure over that signature, on that signature. So it's basically a marriage of a lattice and a residuated monoid. A monoid being residuated means that for the product you have a left division and the right division. Of course, if the product is commutative, then those two divisions coincide. So, in fact, this is a very general definition, and it's quite surprising that despite being such a general structure, we can say very strong theorems in the field of residuated lattices. Well, so I'm going to talk about a few categorical equivalences, and I will confine myself mainly to those where one side is always a class of residuated lattices, often varieties. The other side is something unexpected, mainly group, lattice ordered group or something like that. And, well, the list will not be comprehensive. So the first result is a celebrated result of Daniele Mundici, who proved that MV algebras, the class of the variety of MV algebras, is categorically equivalent to unital abelian L groups. What does it mean? Everybody knows what an abelian L group is. It's called unital if there is a unit which kind of exceeds every other element. So it's a kind of Archimedean property which is assumed in this setting. And an MV algebra is axiomatized by this. It's a commutative monoid. We also have a negation, which is involutive. So we apply it twice. It's the identity. And it has a single element, 0, and this negation is called 1. And there is this Mundici-Chang identity. And in fact, when I mention different categorical equivalences, I will try to go from the specific structures to the more and more general ones. So an MV algebra is a very specific structure in the vast field of residuated lattices. In fact, but you can also measure the complexity of the structure by having a look at the counterpart in the equivalence. In this case, this is all abelian L groups with an order unit. And in fact, the construction is quite simple. You start with a lattice ordered group with an order unit U, and then you take the 0U interval. 0 is the neutral element. And everything which is in between will be the universe of the MV algebra. And what about, for instance, the plus operation? So if you take two elements from this interval, and when the sum exceeds U, you just simply cut it back. So you take a minimum, so a maximum operation. And this is a functor, it's a celebrated result. It had a precursor already in the, well, first let me mention that it appeared in the Journal of Functional Analysis in '86, and I already explained this. And Chang result from 59 appeared in the Transactions of the American Mathematical Society. This is about the same stuff, but only with linearly ordered MV algebras. So where the underlying order is linear. And of course, then the counterpart will be linearly ordered unital abelian L groups. And well, this is how the order is defined, by the way. And let me also mention that sometimes I will show you figures. And this is a binary operation on the real 0-1 interval. And when I show a figure, it means that the structure we are talking about has this member over 0, 1. So if we speak about MV algebras over 0, 1 only, then it is an extremely trivial setting, because there is just a single operation up to isomorphism, which is an MV algebra. You see the dual of it on this picture. So that also suggests, I would say, the trace of the big variety on 0, 1. If it's small, it also suggests that it's not a very general compared to the vast generality of residuated lattices. And by the way, this result has started up a new area of research, and a lot of investigation went to this topic. So for instance, it has been proved that perfect MV algebras are categorically equivalent to abelian L groups. So the strong order unit is missing here. What is perfect? Perfect means that the radical of the algebra, which is as usual just the intersection of all maximal ideals, union, the negation of the radical, has to give you back the whole algebra. That's when the algebra is called a perfect one. So if you assume the algebra, MV algebra is perfect, this class is equivalent to abelian L groups by Di Nola and Lettieri in this journal. And well, if let me just proceed here. If you move from perfect MV to perfect GMV, G stands for general. By the way, MV stands for multi-valued. MV algebra, multi-valued algebra. GMV general multi-valued algebra. Perfect GMV algebras are categorically equivalent to lattice-ordered groups. This appeared in Communication in Algebra. And a generalized MV algebra, or GMV algebra, is a residuated lattice which satisfies that single but very strong axiom. What more? Pseudo MV algebras. When you say pseudo, it means that we are entering the non-commutative setting. So the product is not non-commutative, therefore the two divisions are different. So a pseudo MV algebra is categorically equivalent, as one would expect, to unital L groups. Previously we had unital abelian L groups. It's just L groups. So here everything works as expected. In fact, the construction is the very same. You represent the MV algebra as an interval inside the lattice-ordered group. Well, it appeared in the Journal of the Australian Mathematical Society. And, well, also there are Riesz MV algebras, and those are categorically equivalent to Riesz spaces with a strong unit. And this is a vector lattice analog of the Mundici equivalence. The algebraic models are described as intervals in a Riesz space, and the morphisms correspond to appropriate unital linear, lattice linear maps, which also respect the scalar multiplication, and so on. Well, this annals of pure and applied logic. And there are results about, categorical results about finitely presented MV algebras. They are dually categorically equivalent to rational polyhedra with Z maps. So affine geometry comes into the picture in this point. In fact, well, there is what is called a famous, McNaughton representation of free MV algebras. By the way, what is a finitely presented MV algebra? You take the free MV algebra over n generators, and then you take the quotients generated by finitely many relations. And that's what is called a finitely generated MV algebra. And a rational polyhedron is a finite union of simplices in the n-dimensional Euclidean unit cube with rational vertices. And the Z map is a continuous piecewise map between two such polyhedra. In fact, these two settings are dually categorically equivalent. Well, it appeared recently in the Journal of Logic and Computation. Well, we can speak about cancellative hoops. Those are equivalent to positive cones of abelian L groups. What is a hoop? It's here. It's a commutative monoid, residuated. And this is an important axiom. It's called divisibility. Something like it's not exactly divisibility, but, well, in this setting, it implies divisibility. And also it's cancellative. So we have two very strong conditions. And under these two conditions, a residuated lattice is a class of residuated lattices satisfying this is categorically equivalent to the positive cones of abelian L groups. And I stress the word abelian because the next result is about L groups, so you don't see the abelian word there. Negative cones of L groups are categorically equivalent to cancellative integral, so-called general MV algebras. You have already heard about that. What is integral? Integrality for a residuated lattice means that, you remember, we had a monoid. It had a unit. If the unit element is the top element of the multiplication, you call the structure integral. Cancellative is what you think it is. And so the negative cones of L groups are categorically equivalent to residuated lattices, which are cancellative integral and GMV or GBL. By the way, GBL is a new notion. A generalized BL algebra is a residuated lattice satisfying this axiom. Over 0, 1, a BL algebra looks like this. So we have the minimum operation here. And for instance, this is a linear transformation of a copy of the product in 0, 1. And this is the linear transformation of the MV algebra you have seen before. So the general theorem says that a BL algebra can be represented as such an ordinal sum, where each summand is either the product or a Lukashevich or an MV algebra. And you can have infinitely many here if you like. So you can see that we are entering a slightly more general setting here, because already on 0, 1 we have more, not just a single isomorphic structure satisfying this property. Well, it's algebra universalis, 5 people. And there is the product, the class of product algebras. Well, it's a category built from Boolean data plus a cancellative hoops. Cancellative hoops are, you might remember in the previous slide, where are cancellative hoops? Yeah, those are positive cones of abelian L groups. So if you combine Boolean data with positive cones of groups, then this setting is categorically equivalent to what is called a product algebra, whatever it is. Well, there is just a single product algebra over 0, 1. GMV algebras, well, previously, in the previous slide, so here we have integral GMV algebras. Here we had cancellative integral GMV algebras. Cancellation is a very strong property. And if you skip it, if you drop it, you enter the field of integral GMV algebras. They are categorically equivalent to ordered groups with a conucleus. And a conucleus is a mapping, which is an interior operation, if you see the analogy from topology. So it's sorry, I never know which is the, probably this one. So it's a monotone, contractive, and idempotent operation with this additional property. If these 4 are satisfied, it's called a conucleus. And if you start with an ordered group, you take a nuclear image. It's something like a homomorphism, but slightly different. Then what you get is an integral GMV algebra, and you can do the construction also backwards. What else? Well, I'm not going to tell more about this Journal of Pure and Applied Algebra paper. And now we kind of finished the setting where the so-called divisibility axiom was assumed. Divisibility is a very strong axiom, and that was basically responsible for making these results possible. Because residuated lattices are extremely general, and finding a connection to groups is a rarity. Because lattice-ordered groups is a very specific structure compared to residuated lattices. So far, in all structures, we assumed divisibility. And here, there comes the other strong assumption, which is idempotence. If the monoidal operation of the residuated lattice is idempotent, then this is also a usual setting where some results can be expected, at least. And an example is the class of odd Sugihara monoids. They are categorically equivalent to relative stone algebras, as established by Galatos and Raftery in the Journal of Pure and Applied Algebra. what is a Browerian lattice, Browerian algebra? Well, it's an algebra over that signature. It's a bounded joint semi-lattice with top 1. It's also residuated, but in the residuation law here, you see the fusion, the product. And here we have the meet operation of the lattice, which means that in this setting, you don't have the freedom to choose the product independently. It is always equal to the lattice operation. So here you set the monoidal operation to be equal to the lattice operation of the underlying lattice, of the residuated lattice. And the Stone algebra is just a semilinear version of it. This is the semilinearity axiom. The role of it is quite simply, if you assume it, then such a semilinear algebra can be described as a subdirect product of linearly ordered algebras. That's the advantage of assuming prelinearity. And what is an Odt-Sugihara monoid? Well, you start with a commutative residuated lattice with normal residuation. You also assume you have a negation, a unary operation, which is involutive. And you assume idempotence of the monoidal operation. And you also assume that the negation of the unit element is the unit element. That the unit T here stands for the unit element of the multiplication. So it's also a very restrictive setting if the 0-1 interval is considered, but it's quite difficult to deal with if the whole class is considered. And these two classes are equivalent. So let me show you some axiomatization relevant to the class of residuated lattices. But so the first 3 examples had the divisibility axioms. Sorry, I don't have time to go to the details. This example had cancellation, cancellation, strong, strong, cancellation, cancellation. It's also BL. Odt-Sugihara monoids has the strong property of idempotence. And the last 2 examples are connected to my work, and I only have 3.5 minutes to complete it.
I think you have more time because we started a bit later.
Yeah, thank you.
Like,
right. I will try to do my best. So I investigated odd involutive commutative residuated chains. In this setting, odd means as before. Chain means that the order is total. Notice the lack of assuming divisibility and the lack of assuming the idempotence, the usual 2 very strong axioms. So we are in a very general setting with the additional assumption that the order is linear. And what is an even involutive residuated chain? So if the structure is odd, then the negation of T is T. If the structure is even, then the negation of T is F, which is immediately below T, and there is a gap in between. That's basically what it means. So odd, they coincide. Even, they almost coincide. By the way, for an odd structure, a group is an example. If you take the negation of the unit element, which is in the middle, it's also in the middle, so it's the same. So what about the structure of odd involutive, commutative, and even involutive commutative residuated chains? And those are categorically equivalent to direct systems of abelian O groups with a few extra properties. And what is the functor? Let me describe the basic idea. The basic idea is called the layer decomposition of residuated lattice. And in fact, it considered the equivalence relation defined by this. Quite surprisingly, in case of the structures I started to investigate with, these equivalence classes are closed under the operations of the residuated lattice, except they don't have the constant T and F, which are in the signature. So these equivalence classes contain what is called integrally closed subalgebras of the constant free reduct of X, indexed by the positive idempotent elements of X. So I cut the original algebra to layers, and each layer contains a single positive idempotent element, U. And according to whether U is the unit element or its idempotent and its involutive complement, U prime, that formerly was denoted by negation U is also idempotent, or is idempotent and U prime is not idempotent, so we have three cases to deal with. The algebra XU, the layer algebra, the U layer algebra, is an integrally closed even or odd involutive commutative residuated chain satisfying additional properties. In case 1, it is readily an abelian ordered group, and totally ordered abelian group. In case 3, it is also a totally ordered abelian group, which is in addition discretely ordered, like the integers. Everybody has its neighbor, up and down. And in case of 2, one has to take a nuclear image, and the nuclear image becomes a group. But the nucleus you take the nuclear image with is small. It does something like this. It identifies 2 elements, so maps 2 elements here and there into 1. And before there is no much loss of information from the image, you can reconstruct the layer. So from the layer algebra, you can prepare a layer group. But since not much information is lost, so to speak, you can do this procedure backwards. So you get groups, totally ordered abelian groups in the end. And for 2 positive idempotents, U and V, you can define a homomorphism from the U layer group to the V layer group by sending X to, sorry, it's a mistake, X times V, X multiplied with V. So multiply X coming from this by V, which is the index of the second one. And then you get a direct system of abelian O groups with some additional structure. What else? So something like this. This is the algebra we started with. We cut it into layers, layer groups, and there are the arrows represent between them the homomorphisms. By the way, you can judge the complexity of this algebraic structure by having a look at the other side of the categorical equivalence. There is so much room of freedom in composing homomorphisms between totally ordered abelian groups. So, and therefore, this shows that direct systems of totally ordered abelian groups are extremely difficult, can be extremely difficult. There are many models, non-isomorphic models, and that shows how general this structure we started with is. What about the functor? For the functor, you also need to map homomorphisms, the morphism to the other side, to the morphisms of the other side. Well, according to Fuchs, if you have a direct system here and a direct system there, then a direct system homomorphisms is something like this. Every element here is mapped to an element there, and these squares are commutative. And it cannot be the case that this one and this one are mapped to the same element. This is why it is called an order embedding and not just an order homomorphism. And this is the general Fuchs definition of a homomorphism between direct systems. In our case, the situation is quite unfortunately somewhat more difficult than that, because a bunch, let's call this direct system of layer groups bunches for brevity. So between 2 bunch of layer groups, a bunch homomorphism is a direct system homomorphism with the exception of this condition, but because previously you had here O order embedding, and here it is just order homomorphism. So in our case, if you have a direct system on the left and direct system on the right, it can also be the case that 2 structures are mapped to the same one on the other side. Plus, so to this extent, it's more general than just the general definition, but to the following extent, it is more specific, because these mappings from the one direct system to the other system has to preserve the least element of the indexing set, has to preserve some groups, subgroups, and complement. I haven't talked about this. When you take a nuclear image, I already mentioned that 2 elements I mapped into 1. Color those elements by red. And if you collect the red elements in the new structure, it's a subgroup. When you want to, from the group, reconstruct the layer algebra, you have to know which elements must be doubled. Because if 2 elements is mapped into 1, you color it by red, then inside the structure you obtain, some elements remain unchanged, but some elements go to 2 elements go to a single one. And if you color those elements by red color, they form a subgroup. And in the reconstruction phase, you have to know which elements, the red ones, are those to be doubled to get back the original universe. So sometimes you need subgroups, and in fact, it has to respect the subgroups. It has to respect the neighborhood operation in case discrete abelian, totally ordered abelian groups are considered. It was, I think, case 2, if I remember well. And it has to be partially injective in some sense. And if you do so, then the factor goes like this. You take a normal residuated lattice, an involutive FLE, a residuated lattice homomorphism, which also preserves this F, so phi, and you restrict it to this GX. Then you get a bunch homomorphism. Why? If you have a direct system of groups, what is the universe of the original algebra you started with? So in this direct system, you just simply take the union, the disjoint union of the universes, with the exception of the nuclear image case. Because before there, in this nuclear image case, when some two elements went to some one element, you have to double them before. But this procedure of identifying two elements by one can be described alternatively. You may also say that you get rid of one of them, and just one remains. Then you can also consider it as a subset of the original algebra. You see? And therefore, you can restrict the homomorphism between the original algebras to this subset, and this gives you the bunch homomorphism. By the way, this work has appeared in these two papers. Here is the algebraic correspondence, and here is the functorial analysis of them. And there are two follow-up papers of mine, because this technique, so the class of odd or even involutive FLE chains is very difficult to handle with. But on the other side of the categorical equivalence, we have ordered abelian groups, which are much better known structures, a direct system of them. And there is a hope to cope with some open problems concerning the former structures by using this direct system of totally ordered abelian group structures, by using bunches. And indeed, one can handle densification. It means that densification is the problem of embedding you have a class of algebras, and it's a densifiable class if any algebra from the class can be embedded in a densely ordered algebra in the same class. So these kind of questions can be solved by using this technique, by this categorical equivalence. And also, one can solve the amalgamation problem in these classes. I don't have the time to go into the details what amalgamation is. It's an age-old algebraic notion. You can speak about amalgamation more, for instance. And also, concerning the layer algebra approach, what I introduced, these are the follow-up papers of others who use the same method for other kind of residuated structures. So it seems to be a revolutionary idea in this setting. Well, thank you very much for your attention.